Alright, in this module we're going to talk briefly about how computers actually understand the programs we write. And I wanted to start this module off by talking about this idea that a lot of people have when it comes to programming, and that's that you need to be really good at math because there's lots of numbers in programming. You know, everyone's talking about the ones and zeros that computers have to know to be able to run your programs. And to be completely honest, if all of us programmers had to understand the ones and zeros, which is binary encoding, we would never be able to program anything. It would take us so long to be able to write programs that are as complex as the ones we need to write today if all we could do is write in ones and zeros for a computer to understand. So fortunately for us, programming languages have come a really long way. We no longer have to think about programming computers in terms of ones and zeros. We don't have to think about assembly instructions that would run at the processor level for the processor to go execute. And even some of the earlier programming languages that are still used today have actually had enhancements to them in follow-up languages that have a lot more abstractions and in theory should make them easier for people to write programs in. Over time, these layers of abstraction keep getting added, and the goal is that they're supposed to help simplify the lives of programmers. And the beauty of all of this is that as our lives as programmers are improved by having these higher level languages, we have tools that are able to take our code that we write and actually still convert that into something that a computer can understand. So it's not that computers are getting better at understanding our higher level languages we're using, but we have tools that can allow us to convert those higher level languages into the ones and zeros that a machine can use to run your code. Now, there are whole fields of software engineering that get into these tools that can take our high level languages and turn them into software that computers can actually run directly. And for us, a lot of the time, we don't actually have to think about that, which is great. If you have an interest in it, I think it's awesome that you can dig into this stuff and actually learn some of these really low-level concepts. They actually might be able to teach you some different optimizations and have a better understanding of the languages you're using. But fortunately, you don't have to be able to know all the details to be effective as a programmer. So generally, we're looking at two different flavors of these tools that we're able to use, and they're called interpreters or compilers. Now, this is going to be a huge generalization, but compilers are something that can run and actually take our code once we've typed it all out and actually compile the code, and they're going to translate that code into something that can be used by the machine. This is all done ahead of time, and I am oversimplifying it because a lot of the time compilers have to do multiple passes. Sometimes they're compiling things into yet another intermediate step that's not the low-level code that a machine is going to use to run, and there's something else that can go interface with that. So it is an oversimplification, but compilers are going to be something that runs once your code is done being written, and then it's sort of compiled, it's bundled after it's been transformed into something that the machine can run. Interpreters, on the other hand, are a little bit more on the fly in comparison to compilers. So sometimes you'll hear about programming languages and scripting languages, and a lot of the time a fundamental difference here is that scripting languages aren't necessarily compiled. Again, I'm generalizing here, but instead on the fly, as the computer's executing the code, it will actually interpret the language that you wrote in and actually have instructions that the machine can go execute. Again, another generalization here is that interpreted languages are usually slower, not always the case, but that's generally the side effect of having it interpreted on the fly. And other times people will say that these compiled languages are much faster because there's optimizations that can be done well ahead of time based on the sets of rules that the compilers know about. And there's also hybrid approaches too, where we have just-in-time compilation. So you have kind of this mix of feeling like some pieces are interpreted or getting the benefits of an interpreted language because it's not all compiled ahead of time. But like I said, there's whole fields of software engineering that really focus on these parts. So just to recap before we finish off this module, fortunately for us as programmers, if we don't want to think in ones and zeros, because not a lot of us do, you don't have to worry about writing code in ones and zeros for computers to understand. Instead, we have a lot of these high-level languages, and there are tons of them for you to pick from. And these high-level languages actually get converted into something else by tools that the computer can understand. So do you need to be a math whiz to be able to program? No. If you are programming in an industry that requires a lot of math, yes, you probably want some math background. But I can say that a lot of the complex math that you're going to be doing is actually just counting things. So if you can count, you can do a lot of different things in programming, so don't sweat it. That's all for this module. Thanks, and let's move on to the next.